And all right, we are live. So we're going to do the end of chapter problems, chapters 4 and 5. Let's see if we can't bang these out in less than 2 hours. All right, so first up is problem 32. What general trends in electronegativity occur in the periodic table? All right. Really straightforward. They follow the exact same trends as ionization energy and electronegativity. So every step you go up on the periodic table is a step or a step to the right. Either one of those is going to increase your electronegativity. Who's next? 34, 36, 38, 40. Okay, so we're just going straight through to 40. Okay, 34. Order the following elements according to increasing electronegativity. Lithium. Okay, I'm going to have to write these down because I'm going to hop over to the periodic table next. Lithium, bromine, lead, potassium, magnesium, and carbon. Okay, so periodic table. So lithium versus bromine. Bromine is going to win. Bromine versus lead. Bromine is going to win. Bromine versus potassium. Bromine is going to win. Bromine versus magnesium. Bromine is going to win. Bromine versus carbon. Ooh, that's a tough one. Let's see. Can I get this to show me electronegativity? I do not see that it can. It does list electron affinity. Oh, electronegativity is 2.96 for bromine, and carbon is 2.55. So bromine is going to win. All right. I was uncertain about that, but bromine is going to be number 1. That's right. I wanted to turn on the camera. So bromine is number 1. Carbon is going to be number 2. Lithium versus magnesium. I'm going to go with lithium before magnesium, and then potassium, and then lead. Yeah, lithium, magnesium, potassium, lead. So let's see, it was 2.96, 2.55. Let's see, lithium. Lithium is 0.98. Magnesium, 1.31. Oh, I got that wrong. So magnesium should go up. Potassium, 0.82. And then lead, 2.33. Oh, wow. Okay. So lead goes higher. All right. So it looks like taking a step to the right makes more of a difference than taking a step down on the periodic table. Okay, so next up is 36. Which of the following substances are largely ionic and which are covalent? Okay, so hydrogen fluoride is covalent. Hydrogen iodide is covalent. Palladium chloride is going to be ionic. So the way I'm judging this is just not two nonmetals is going to be covalent. A metal and a nonmetal is going to be ionic. So palladium chloride is ionic. Boron tribromide is covalent. Sodium hydroxide is ionic. Then methyl lithium. Ooh, that's a tough one. Organic or metallo-organic compounds. Not something we typically cover. I'm going to say that one is going to be very unhappy for one thing. Very, very unhappy. So, but I'm going to call it covalent. Yeah, that's a weird one. Surprised they would include that one on there. But it might be ionic. I mean, just the fact that you have a metal bound to a nonmetal. And the fact that it's a carbanion. Oh, wow. Yeah, but, I don't know. Simple rules, go ahead and call it ionic. Don't need to get fancy. Show the direction of polarity for each of the bonds in problem 437 using the partial negative, partial positive notation. All right. So we have 6 bonds to look at. First up, we have carbon, hydrogen. That one's just nonpolar. Carbon and chlorine. Chlorine is more electronegative, so it's going to be partial negative. Carbon's going to be partial positive. Silicon and lithium. Well, that in fact would be ionic. But let's go ahead and say delta negative, delta positive. Silicon and chlorine. Chlorine is more electronegative than silicon. Nitrogen and chlorine. Ooh. I'm going to go ahead and say that nitrogen is more electronegative than chlorine. I might be wrong about that, but I don't think I am. So let's see. Nitrogen, 3.04. Chlorine, 3.16. Oh, I was wrong. But so close that, in fact, I'd call it nonpolar because it's a difference of 0.12. And between 0 and 0.4 is when it would be nonpolar. All right, and finally, sodium and magnesium. In fact, that would be ionic, probably. But sodium, or not sodium, but nitrogen and magnesium. Magnesium nitride is going to be an ionic compound. All right, 440. Which of the substances listed are ionic, nonpolar, or polar? So we have palladium chloride, phosphorus, bromine tetrafluoride, trifluoride, magnesium oxide, nitrogen trifluoride, barium chloride, POCl3, and lithium bromide. All right. So which are nonpolar? So for nonpolar, I'm going to do blue. Phosphorus is nonpolar. That's going to be it. All right. For polar covalent, I'm going to go ahead and do purple. Polar, polar, polar. And then for ionic, I'm just going to go ahead and do red, and that's going to be the rest of them. Metal, nonmetal, metal, nonmetal, metal, nonmetal, metal, nonmetal. All right. Okay, now that got us there. So 46, 48, 50, 52. Okay, we're just going to go straight through to 52, starting at 46. Name the following molecular compounds. Okay. Well, we have phosphorus trichloride, dinitrogen trioxide, tetraphosphorus heptoxide, bromine trifluoride, nitrogen trichloride, tetraphosphorus hexoxide, disulfur difluoride, and selenium dioxide. Write the formulas for the following molecular compounds. Okay, I'll go ahead and turn the camera back on for this one. Disulfur dichloride is going to be S2Cl2. Iodine monochloride is ICl. Nitrogen triiodide is Ni3. Dichlorine monoxide is Cl2O. Chlorine trioxide is ClO3. And tetrasulfur tetranitride is S4N4. Why does the octet rule apply primarily to main group elements, not to transition metals? Because transition metals have d block electrons, and those d block electrons, or sorry, d group, d level, d sublevel, d electrons. We just call them d electrons. D electrons, go up to 10. We have the degeneracy playing a major role in there, giving them oddities. They have access to empty orbitals all over the place. They just behave in a very different fashion. So they're not going to end up acting in the same way. And I believe 52 was the last one. Yes, 52 is what we're going to next. 52. Draw electron dot structures for the following molecules or ions. First up, we have carbon tetrabromide, CBr4. I'm not going to go through and do this stepwise, but I will show you the correct answers. Okay. There's carbon tetrabromide, simple Lewis structures. Nitrogen trichloride. All right, C2H5Cl. Okay, CCCl, H, and then 3 lone pairs on chlorine. BF4 1 minus. Let's see, so boron gives us 3, fluorine gives us 7, so 28 plus 4 is 32. Okay. B, F, 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 F. One minus. All right, and finally, I believe we have 2 more. First up is going to be peroxide, and then not quite nitric oxide. So O2, 2 minus, that means 14 electrons. Really? Okay. But I believe that's going to be, yes, 2, 4, 6, 2, 4, 6. Peroxide is a very unhappy molecule, but it's very reactive. Okay, so next up is NO+. That's going to be a total of 10 electrons, so I believe... Two, 4, 6, 8, 10, 12. Ooh, no. Did I screw that? Let's see. 6 plus 5 is 11. Yeah, so... Ooh. Single bond. So let's go ahead and bring this in like that. Okay. 2, 3, 4. 1, 2, 3, 4, 6. Yes. Yeah. I did it like this because when you check the formal charges, you'll see that this way oxygen has a 0 formal charge and nitrogen has a +1 formal charge. Oxygen is more electronegative, so it will not get the positive formal charge. Wait, no, that way nitrogen doesn't have a full octet. What am I thinking? Boom. So now, that's gonna 0 and +1. Ugh, that just makes everyone unhappy. Well, it is an uncommon weird-ass ion. Now everybody has a full octet, but yuck. All right. So next up, 58. Write electron dot structures for molecules with the following connections, showing lone pairs and identifying any multiple bonds. Okay, that's fairly straightforward. In order to make these molecules happy, knowing about valency helps. So let's see, we have chlorine, carbon, oxygen, carbon, hydrogen. Okay, that's a pretty interesting compound right there. Okay, the reason I put the double bond there is because oxygen needs the 8 electrons, and carbon likewise. So it's not going to form a double bond with chlorine because chlorine does not care for that. This oxygen has 2 lone pairs. Yeah, this is fairly straightforward. All right, next up we have this guy here. H, C, 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 H, H, H. The only way this works is if you have a triple bond in between those 2 carbons. Because otherwise they would have other things bound to them. And they're not going to have lone pairs. Okay. It's a lot easier to do it that way than it is to count electrons for that sort of molecule. All right, who's next? Who's next? 58, 60. Well, we're just going to go straight through to 70. Okay. Methylphenidate, C14H19NO2, marketed as Ritalin, is often prescribed for attention deficit disorder. Complete the following electron dot structure. Holy crap. Okay, all right. Oh, man, this is a beast. Okay, so let's see if I can fit this all on a single page. Let's see, we have carbon, 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 oops, carbon. Then it is bound to another carbon here. Carbon, oxygen, oxygen. This oxygen is bridging to a methyl group. Then this carbon is bound to yet another ring. It's also got a hydrogen here. Oh, that's a pyridine ring, looks like. So there's nitrogen, carbon. Oh, it's not a pyridine ring. It is a six-membered ring, but it is loaded with hydrogens. It is saturated. Okay. This carbon also, yes, has a a hydrogen, 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 hydrogen. Okay. So this guy is going to have alternating double bonds. It is a benzene ring. 1, 2, 3, 4. Yes, good. This oxygen is going to need double bond and lone pairs. This oxygen is going to need lone pairs. And this nitrogen will need lone pairs. Okay. So that's Ritalin. Interesting. A desaturated pyridine ring, or a saturated pyridine ring, and then a benzene ring. Okay. I did not know that's what Ritalin was, and I will probably forget it very, very quickly. That's not the sort of thing that you recall. Okay, so draw as many resonance... Oh, by the way, those alternating double bonds would have resonance. So another way to draw it would be with the double bonds on the other three positions. All right, draw resonance structures, as many as you can, that obey the octet rule for each of the following molecules or ions. HN3. All right, HN3, that's different. HN3. So, let's see, let's try a linear one. So we have 15, 16 electrons, so 2, 4, 6, 8, 10, 12, 14, 16. That makes a lot of people very unhappy. Let's try putting that there instead. Let me turn, let's see, 2, 4, 6, 2, 4, 6. Yeah, there's really no way to make everyone happy like this, so it's not going to be that. Let's see, N, H, maybe? 2, 4, 6, 8, 10, 12, 14, 16. No, that ain't going to hunt either. HN3, that is weird. Maybe the only way to do this is to make it a ring with a hydrogen coming off one corner. So let's see, 2, 4, 6, 8, 10, 12, 14, 16. And then we make this into a double bond. Oof. Oh. Oh, that's nasty. But 2, 4, 6, 8, 10, 12, 14, 16, octet, octet, octet. It works, but man alive, is it ugly. Ooh. Oof. I'm going to check the appendix on that one. this. Dang, I do not like it. We're on page 164. Let's see if I can remember that. Appendix, answers to... Oh, I don't want that. I want answers to selected problems. There it is. All right. Problem 4, 6 to 2 is what we're looking for. No, they did linear with a triple bond in the middle. Or with a double bond going between the two. Huh. So 2, 4, 6, 8, 10, 12, 14, 16. Yeah, that is... Or triple bond on that side. Okay. Huh. Okay. I would simply never have thought of that. Okay. All right, next up we have SO3, sulfur trioxide. In fact, I don't think it will have resonance. I mean, what they're going for is an uncorrected structure that looks like this. But the reality is when you look at formal charges, -1, -1, +2, yeah. So the actual structure is that. 3 double bonds, so no resonance. But, I mean, they're going for a single double bond that resonates around the entire thing. But I'm pretty sure the actual structure is that bad boy. Next up, SCN1-, thiocyanide, or sorry, thiocyanate. SCN1-, so 6 + 4 + 5 is 15, and 1 more makes 16. 2, 4, 6, 8, 10, 12, 14, 16. Okay, so these are the 3 structures that they are expecting us to come up with for thiocyanate. This one's very straightforward. Yeah. Let's see. +1, 0, -2, 0, 0, -1, -1, 0, 0. This one is the preferred one, just if you're looking at formal charges. Because, let's see, +1, 0, -2. Ew. This one is 0, 0, -1. This one's -1, 0, 0. And nitrogen is more electronegative than sulfur. So nitrogen is going to be the one with the negative formal charge. All right. I believe we're going straight through to 70. So 64. Which of the following pairs of structures represents resonance forms and which do not? Let me go ahead and get rid of this. HCN and O. This is not resonance because this leaves carbon without a stable octet, so it's not going to do that. This, likewise, is not resonance. It leaves sulfur without the octet. This one would be. This is a feasible resonance structure. Because this carbon still has the stable octet with this lone pair on it. And this one likewise. So C and D are resonance structures, A and B are not. Draw an electron dot structure for carbon monoxide and assign formal charges to both atoms. All right, so here is, I'm going to need to turn the camera back on. Carbon monoxide is this bad boy right here. And the formal charges we get are 4 minus 5 is -1. 6 minus 5 is +1. So you can see why carbon monoxide is not the happiest, most stable relationship between carbon and oxygen. It is. It tends to break down over time. Not super quickly, but it does tend to break down. It's not the happiest thing in the world. All right. That was 66. 68. Assign formal charges to the atoms in the following resonance structures of hypochlorite. No, that's just, yeah, that's chlorite. All right, so ClO1 minus. So we have chlorine bound to 2 oxygens with 2 lone pairs. Wait. Okay. And then we have chlorine bound to the oxygens like this. Chlorine is in the 3rd row, so it can go beyond the full octet, so it can do this. I believe this lower structure is going to be the one that's happier. So our oxygens start with 6. Well, so this oxygen is -1, so is this one. Which means chlorine here has to be +1. It started at 7, 2, 4, 5, 6. Yes, it's at +1. This one is -1, this oxygen is 0, and now chlorine is also at 0. 2, 4, 5, 6, 7, yes. So this is the happier structure. Chlorite has resonance. Oxyanions often do have resonance. It's one of the reasons they're so common, why they exist. All right, 70. Assign formal charges to the atoms in the following structures. Which of the two do you think is the more important contributor to the resonance hybrid? Well, obviously the one on the left. It has the stable octet, you'd think. All right, so we have hydrogen, carbon, hydrogen, nitrogen, nitrogen, hydrogen, carbon, hydrogen, hydrogen, nitrogen, nitrogen. Okay. So in both cases, our hydrogens are going to have formal charges of 0. They are perfectly happy just with that bond. Here, carbon is 0. Here, it is +1. And it doesn't have the full octet. It has just an empty p orbital hanging out there, just begging for something to come in and bond. Here we have +1. Here we have 0, -1, -1. All right. So just according to formal charge rules, they don't ask you to judge based on the presence of the stable octet. But just by formal charge rules, this down here is the happier structure because nitrogen is more electronegative than carbon. So you want the positive formal charge on carbon according to formal charge rules. That is wild. That is absolutely wild. Okay, let's move on to chapter 5. I'm starting with problem 18. Oops. Okay, so molecular shape, handedness, and drugs. Acetamide. All right. What is the geometry around the central atom in each of the following molecular models? Okay, this should be easy peasy for you all by now. This one here is square pyramidal. This one is trigonal pyramidal. This is square planar, and this is trigonal planar. Boom. Boom. Dang it. What happened to... There it is. All right. 2024. 3 of the following molecular models have a tetrahedral central atom, and 1 does not. Which is the odd one? There may be a hidden atom directly behind a visible atom in some cases. A is tetrahedral. It's hard to see on the video probably, but there's an angle to the bonds. This one is also tetrahedral. It's hard to tell, but there is a carbon atom hidden directly behind the hydrogen atom there. You can see a black ring around that white sphere. This one is not tetrahedral. That's just a flat square. This one, it has a tetrahedral central atom, even though there is a lone pair on that guy. So it's a trigonal pyramidal structure, but there is a lone pair. Okay. 24. What geometric arrangement of charge clouds do you expect for atoms that have the following number of charge clouds? 3 is going to be trig planar, 5 is trig bipyramidal, 2 is linear, and 6 is octahedral. This is just an exercise in memorization, so they're just getting you to practice that, work on that, memorize that. 26, 28, 30, 32, 34, 36, 38. So we're going straight through to 38. How many charge clouds are there on the central atom that have the following geometries? Same thing, other direction. Tetrahedral is 4. Octahedral is 6. Bent could be either 3 or 4. There are 2 bent geometries. One is 3 charges, 1 lone pair. The other is 4 charges, 2 lone pairs. Linear, again, there's a number of possibilities there. It could be straightforwardly linear with just 2 charge clouds or electron domains. It could be trigonal bipyramidal, 5 domains and 3 lone pairs, or it could be octahedral, 6 domains with 4 lone pairs. Square pyramidal is just going to have 6 electron domains, 6 charge clouds. And trigonal pyramidal is going to be 4 domains, 4 charge clouds. Each of those has 1 lone pair. 28. What shape do you expect for each of the following molecules? Okay, H2SE. Okay, H2SE looks like this. So it is going to be bent. Selenium is 2 below oxygen, so it's very similar. Titanium tetrachloride. Let's assume for the moment that it is not ionic. Let's treat it as a molecular thing. That's kind of weird. But let's pop over to the periodic table. I believe titanium will have, yes, 4 electrons. So 4 plus 28 gives us 32. So it is going to be tetrahedral. If it were a molecule, this is odd. Okay, who's next? O3, ozone. Oh, ozone's a different one. Ozone is going to be bent, and it is going to have resonance. So ozone is kind of a weird molecule. No charge, but yes to resonance. Okay, was that the last one? 28? Nope, we also have gallium trihydride, or gallium. Gallium? I don't know. GaH3AHH. Gallium should be giving us 3 electrons. So this, I think, would be trig planar. I would expect it to behave similarly to boron in this case. It is in the same group as boron. Okay. Actually, let's go ahead and check the appendix. Some of those are weird. Let's see what the book says. What do the books say? We're on 28, I think. Bent, tetrahedral, bent, trig planar. Oh, I forgot to say, yeah. Ozone is bent. I was too distracted by the fact that it was an interesting molecule. Okay, so, yep, trig planar. I got that right. All right. Okay, so I forgot to memorize the page, so we're going to have to go back the slow way. Actually, I can probably speed it up. Boop. 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 Nope, one more boop. Nope, another boop. Oh, that, okay. Let's see, that was 28. 30. What shape do you expect for each of the following molecules or ions? Stibium Antimony pentafluoride. Uh, boop 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 boop. Boop 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 boop. Boop 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 boop. All right, and let's see. Antimony is in the same group as nitrogen. Yeah, so 5 plus 35 means 40, so this is the thing, so it is trig-bippy. This is trigonal bipyramidal. Iodine tetrafluoride 1 plus. So that's going to be 34 electrons. It's going to be a seesaw or disphonoidal. We have a total of 32 electrons, or sorry, 34 electrons. And so iodine has a lone pair. That makes it disphonoidal or seesaw. SeO3 2 minus. So let's see, that's 18, 24, 26 total electrons. So that is going to be trigonal pyramidal. And it will also have resonance. They're not asking you to check formal charges on this one, but I'm going to go ahead and do that because I can. All right, and next up, and finally, chromate, CrO4 2 minus. Let's see, chromium should give us 7 electrons, I think. It's in the middle of the periodic table. 1, 2, 3, 4. It gives us 6. So that's going to be 30 total electrons, and then 2 more. Yeah, so... Oh, but that chromium is very unhappy, so we're going to have a couple of double bonds. So it is going to be tetrahedral. Lots of resonance. All right, 32. What shape do you expect for each of the following anions? Well, getting lots and lots of practice for these things is a very good idea. All right. So PO4 3 minus. Let's see, 5 plus 24 plus 3 is 32 electrons. Yep, this is just tetrahedral. Next, manganate, MnO4 1 minus. No, that's permanganate, MnO4 1 minus. Let's see, manganese gives us... That does give us 7. So 7 plus 24 is 31. Okay. And then 1, 2, 3 double bonds. It is also going to be tetrahedral. SO4 2 minus. Again, tetrahedral. Dang, these things are just... Give me something interesting. All right, SO3 2 minus. That one's going to be trigonal pyramidal. S O O O. Let's see. That's 24 plus 2 is 26. Yes. ClO4 1 minus. That's also going to be tetrahedral. Because 7 plus 24 plus 1 gives us another 32. 32 electrons divided among 4 satellites, just the full octet for all 4, so nothing left over on the middle. That's how I'm doing that math real quick in my head. And thiocyanate is going to be linear. Stupid. You have the 3 resonance structures for thiocyanate, and regardless, always linear. All right, and where was the cutoff point for? We're going up to 38. 34. What bond angles do you expect in each of the following? So SF2 is going to be, that's going to be bent, so it's going to be less than 109.5. Into H2. Oh, that is going to be, again, trigonal pyramidal. H in N, yeah. Like this. Into H2. 10, 11, 12, 13, 14, 2, 4, 6, 8, 10, 12. Yeah, no double bond. So let me redraw that on a new page, because that's not clear. So each of our nitrogens is trigonal pyramidal. So our bond angles are all less than 109.5. So that's what the H and N bond angle is. It's also the H and H bond angle, or the, well, that's all. All right, KrF4. Ooh, yes. Krypton is a noble gas, but noble gases can form molecules if you beat the utter crap out of them with fluorine. So 8 plus 28 makes 36, so it has 2 lone pairs. So those are all 90 degrees. That's a square planar molecule. NOCl. Okay, 5, 6, and 7 makes for 18. So NOCl? No, I don't think so. I think it's going to be ONCl. Yeah, it explicitly tells us that N is in the middle there. So 2, 4, 6, 8, 10, 12, 14, 16, 18, and then double bond there. All right, so that's NOCl. So this is a trigonal planar thing. It's bent, so it's going to be less than 120. All right, 36. Acrylyl nitrile is used as the starting material for manufacturing acrylic fibers. Predict values for all bond angles in acrylonitrile. Okay, they give us the structure, so I don't have to draw that out. H2CC. Okay, so the hydrogen-carbon-hydrogen bond angle there is going to be less than 120. It is a trigonal planar thing, because, the carbon has 3 things. So it would be nice at 120, but that double bond squeezes the hydrogens together. Hydrogen-carbon-carbon is going to be a little greater than 120, because, like I said, the double bond takes up more space, so that makes that bond bigger, that angle bigger. Carbon-carbon-hydrogen going to the middle, again, that's going to be bigger than 120. Hydrogen-carbon-carbon going in the other direction is going to be less than 120. Carbon-carbon-nitrogen is linear, because this triple bond, this carbon in the middle just has 2 things, so it's linear. All right, oceanographers, number 38. Oceanographers study the mixing of water masses by releasing tracer molecules at a site and then detecting their presence at other places. The molecule trifluoromethylsulfur pentafluoride is one such tracer. Draw an electron dot structure for CF3SF5 and predict the bond angles around both carbon and sulfur. All right. So carbon and sulfur are bound together and then surrounded by fluorines. So carbon, sulfur. And then we just go in and fill in all these things. And that should be all you have to do, because I'm pretty sure that will use up all the available electrons. I don't think there's any lone pairs floating around on carbon or sulfur. So 4 plus 6 is 10. Then we have 1, 2, 3, 4, 5, 6, 7, 8 fluorines. 8 times 7 is 56. So 66 total electrons. 1, 2, 3, 4, 5, 6, 7. Yes. So wait, 1, 2, 3, 4, 5, 6, 7, 8. Yeah, that uses them all up. 64 for all the fluorines, then 2 more for the bond between carbon and sulfur. So nice and straightforward. Carbon has a tetrahedral center, and sulfur has an octahedral center. Oh, meaning that the bond angles around carbon and sulfur, 109.5 for carbon, 90 degrees for sulfur. Slightly distorted because, this bond here in the middle makes for a slight unevenness. Sulfur just doesn't push back against carbon the way that the fluorines do. So you'll get slight distortions, but not huge. About 109.5, about 90. All right, who comes after 38? 44, 46, 48, 50. So 44 through 50. What hybridization do you expect for atoms that have the following number of charged clouds? Charged clouds are what I've been calling electron domains in class. All right, so 2 means sp, 3 is sp2, and 4 is sp3. What hybridization would you expect for the indicated atom in each of the following molecules? Okay, so oops, you can't see. So for the carbon in formaldehyde, it is trigonal planar, has 3 electron domains, so it is sp2. Borane, boron trihydride, is also sp2. Oh, this is different. CH3SH. I'm going to have to go ahead and draw this one out. It's just sp3. Oh. I'm still going to draw it out. All right. So 6 plus 4 is 10, 11, 12, 13, 14 electrons. So 2, 4, 6, 8, 10, 12, 14. So our sulfur has 2 lone pairs on it, making it sp3. CH3, oh no, where did I, there we go, H2C in H. Okay, once again, they're not showing the lone pairs, which is kind of clever of them. If you just went by this, you might think that nitrogen only had 3 electron domains, but it has a lone pair, so it has 4 electron domains, meaning it's sp3 hybridized. Oxaloacetic acid is an intermediate involved in the citric acid cycle of food metabolism. What are the hybridizations of the various carbon atoms in oxaloacetic acid? And what are the approximate values of the various bond angles? Well, decent practice. All right, so trig planar means sp2 hybridized and around 120 degrees. Trig planar again, so sp2 and about 120. This has 4 bonds, so it's sp3 hybridized and it's 109.5-ish. And trig planar again, so sp2 and about 120. All right, do we also have to do 50? Yes. 50. Bupropion, marketed as Wellbutrin, is a heavily prescribed medication used in the treatment of depression. What are the hybridizations of the various carbon atoms? Okay, just again counting electron domains. The carbons in this ring here all have 3 electron domains. They are all trig planar. They're all sp2 hybridized. This bridging carbon right here is sp2 hybridized, again trig planar. This carbon here, it's tetrahedral, so sp3 hybridized. This carbon is also tetrahedral, also sp3. also. So these 4 carbons up here are all tetrahedral and all sp3 hybridized. Our next problem is number 62. The following molecular model is a representation of caffeine. Identify the position or positions of the multiple bonds in caffeine and tell the hybridization of each carbon atom where the carbon atoms are black. Well, they call them gray, but they look black to me. All right. So you can tell whether there are double bonds because the carbon has an unfilled octet just based on the bonding shown. So like this carbon here in the upper left, it has 4 bonds, so it's perfectly happy. So it has a full octet. So it only has single bonds, so it's sp3 hybridized. This carbon has to have a double bond on one side or the other. There's probably resonance floating around this ring. So it has to be sp2 hybridized. Likewise, these 2 carbons are going to need double bonds. That's why I'm predicting resonance floating around this ring. They're both sp2 hybridized. This guy down here is sp3 hybridized. This one, it has a double bond, but it's on the oxygen. So is this one. It has a double bond on the oxygen. They're both sp2 hybridized. This carbon here has all 4 bonds, so he's good to go. He's sp3 hybridized. And finally, number 64. The odor of cinnamon oil is due to cinnamaldehyde, C9H8O. What is the hybridization of each carbon atom in cinnamaldehyde? How many sigma bonds and how many pi bonds does cinnamaldehyde have? All right, so every single one of these carbons has 3 electron domains. Every single one of these carbons is sp2 hybridized. Just because you see so many, all these double bonds floating around. Yeah, 3 electron domains on every single one of those carbons. So they're all sp2 hybridized. As for number of sigma bonds and pi bonds, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 sigma bonds. 1, 2, 3, 4, 5 pi bonds. All right. And that is it for chapters 4 and 5. I managed to knock them both out in less than an hour. I will start chapter 6 tomorrow evening. And that is what we will be discussing next week. Good luck on your test, y'all. I'll see you around.